Hi, my name is Fomitchev-Zamilov. I am the founder of Maximus Energy Corporation, and today I'm going to talk about ancient Egyptian Predynastic stone vessels. And specifically, I'm going to reveal some of the eye-opening facts about how these stone vessels could have been made. There's been ample speculation about the precision of ancient Egyptian stone vessels on the internet. Countless videos on YouTube, lots of discussion online and offline. And I found all of this fascinating, interesting, and it motivated me to begin the research into ancient Egyptian stone vessels in earnest. I have been studying this subject for the past year. And the more I learned about these stone vessels, the more I was amazed and surprised by the facts that I uncovered. And today I'm trying to put everything I've learned together to give you a consistent picture of what I think was happening with the stone vessels in pre-dynastic ancient Egypt.
Интересно.
So, how did you start working on this project?
About a year ago, I watched one of Ben Van Kerkhoff's videos about the unbelievable precision of ancient Egyptian stone vessels, which really intrigued me. So I wrote to him and I proposed that we do a electron microscopy analysis of his samples of stone vessels. He took up my proposal and visited here in Naples, Florida, and brought some of his stone vessel samples, and we looked at them using my electron microscope. And that's how I got started on the base path.
And what happened next?
Next, I got introduced to Matt Bell, who is the founder of Matt Bell's Limitless podcast on YouTube. And he also happens to be a collector. So he collected 80 or about 88 ancient Egyptian stone vessels. And he lives also in Florida, not far from where I live. So I reached out to him, and he shared some of the 3D scans of the vessels in his collection with me. And I wrote some code to analyze those vessels, and I was surprised to see how precise and pristine the 3D scans were. So in fact, what I have seen basically corroborated Ben Van Kerkhoff's claims that he made in his videos, and some other people um, published on internet on how precise and how marvelous these vessels are.
What did you do? How did you analyze the vessels?
I analyzed CT scans. So some people analyze optical scans because it's easier to take a 3D scanner and scan a stone vessel. Matt Bell went a step further. He used CT scanning, which is much more accurate technique, and he produced a ton, like over 40 of 3D scans, basically a 3D model of a stone vessel. And I wrote some code in MATLAB to analyze those scans. And what I have done, I'm loading an STL file, which is a 3D model of a stone vessel in MATLAB, and then my code slices it along the z-axis. And as a result of that slicing, I'm getting pieces of vessel, which are basically circular in nature, and I evaluate how circular and how concentric they are. And based on this evaluation of the entire vessel, of slices of both inner and outer surfaces, I'm able to tell how precisely the vessel is manufactured, meaning how round the slices are and how concentric they are, separately for inner and for the outer surfaces. And that's what the code does. And at the end, it gives a metric. It tells me how precise the vessel is. And I've seen that in Matt Bell's collection, vessels fell into two categories. One category were extremely precise vessels, machine precision, because I was able to compare them to modern day stone vessels, the kind you can buy in gift shops or made by artists. And those are typically made on a lathe using modern technology. So those vessels are extremely precise as far as metrology of them goes. And great many vessels in Matt Bell's collection were as precise as modern day stone vases made on a lathe, which intrigued me immensely. And the other portion of vessels in his collection weren't as precise, basically consistent with manual labor. And for a sample of manually made vases, I used 3D scans of stone vessels made by Olga Vdovina, who recreated ancient Egyptian stoneworking technique uh, in order to prove that these vessels could be made by hand. And fortunately for me, those vessels were scanned were made available, and I analyzed them also to get data points for comparison. So I could compare ancient Egyptian vessels from Matt Bell's collection to modern day vessels to the vessels that were made purposefully by hand using manual techniques by Olga Vdovina. And the result was, nothing short of, shocking for me, because I saw that great many vessels in Matt Bell's collection looked extremely precise.
Can you show me some examples of contemporary vases and the real ones?
Sure. This is a granite vase that I bought on eBay for about, $30, and it's made on a lathe. It's extremely precise, extremely well machined, and it's granite, so it's very hard stone, and it kind of proves that today people have no problem in machining granite into pretty much any shape you want. Here is another vessel, which is more common. It's onyx. Onyx is slightly less hard on the most scale of hardness than granite. And this is your run-of-the-mill, gift shop, vase that's also made on a lathe. Here is another onyx bowl, which is also made on a lathe in a very finely polished, very well machined. So these are very precise. And here's a vase from Matt Bell's collection, which is a basalt vase. And visually, it's not as precisely made as the modern vases that I've showed you. So it's in a different category, but it's a basalt vase from Matt Bell's collection. And here is another one, a real tiny one. It looks like diorite by the looks of it. And it's well made, but not as precise. So it's more like consistent with manual labor. And of course, all of the nicer vases Matt Bell has in his collection. So I borrowed only these two to study.
Please show me how the program works.
Okay, so here is a 3D scan of one of the vessels from Matt Bell's collection. So this 3D scan was obtained by CT scanning of the vase, and the resulting STL file, you can examine it on the computer. You can look at the inner and outer surface, but to really obtain metrological information about this vessel, I had to write code in MATLAB. So MATLAB allows to manipulate matrices and vectors and operate on 3D objects. And the only limitation is your own imagination, what you can do, with the data. So what I have done is I loaded the STL file into MATLAB, and I sliced it into a series of horizontal slices along the z-axis. So on this picture, you can see the cross-section of a vessel, and every blue line is a slice through the exterior surface, and every orange line is a slice through the interior surface. And in this window, you can see those slices from the top. And as I said, because all vessels are cylindrical in nature, the resulting slices are round. And then the software that I developed, it evaluates how round those slices are. So it fits every slice, inner surface or outer surface, it fits it to a circle. And then I plot root mean square errors for the inner surface feet and for the outer surface feet. And this is this window. So blue plot here is the root mean square errors, RMS, in other words, RMS errors for the outer surface, and orange is RMS errors for the inner surface. And as you can see, the outer surface is a bit more precise. The average RMS error is about 1/2 of a thousandth of an inch, which is insane. And the outer surface area here is about, one inner surface area is about 1/1000th of an inch. So besides the RMS error, I'm also looking at how concentric those slices are. So the center of each circle needs to fall on the same vertical line if the object is to be perfectly symmetric. And this is this plot. So I evaluate the shift of the fit of a circle from the origin. And for the outer surface here, that shift is basically 1/4 of 1/1000 of an inch. And for the inner surface, it's about maybe a half, slightly more than 1/2 of 1/1000 of an inch. So in other words, all of the slices are insanely round and are insanely well aligned to where they fall on the same axis. And on this plot, I visualize the scatter, how the centers of the fit circles appear on the XY plane. And it's basically shows how well those slices are aligned in terms of how well their centers are aligned. And we can see here that the blue dots correspond to the outer surface. They're much more compactly aligned than the red dots, which is the inner surface, which is still, pretty amazingly compactly aligned, but not quite as well. So by looking at this object, I can tell that it's very well made. It's very precisely made because it's very round and the slices are extremely concentric. So for every object that I studied in Matt Bell collection, I ran my code, and it took a few hours to get the results, because one of the important parts of analysis was to make sure that the object is optimally positioned vertically, because slight deviations from vertical alignment would impact the results in a negative way. And because there are many ways an object can be oriented, I had to explore rather significant parametric space of all possible tilts of an object to get the optimal alignment. And that what takes most of the time. And that was one of the things that I've learned that are very important. Prior to analysis, object needs to be aligned vertically very, very well. And it's not a trivial task. It cannot be solved easily because these objects aren't like perfect. They're very well made, but they're not like completely mathematically perfect. Therefore, aligning them is a bit of a challenge. And that's what the line portion of the code processing time was, just searching for this perfect optimal alignment, and then for that alignment calculating how concentric and how round the slices are. But that's the code in a nutshell.
What do you want to find in the Petrie Museum?
I want to find the evidence of ancient nuclear machining technology.
And how would you do that?
I will measure gamma and alpha spectra of the stone artifacts in Petrie collection.
That's cool. We'll see if it happens.
I hope so.
After you completed your research of the private art collection, what did you do next?
After examining the objects from Matt Bell's collection, I decided to go to the Petrie Museum in London because I wanted to look at some of the museum objects to see how they would compare to objects that are privately owned. And that was a rather significant undertaking because in order to go to a museum, I had to get a 3D scanner. And there are a lot of 3D scanners on the market, and they are meant for reverse engineering, for architecture, for sculpture work. There are very few that are metrology grade instruments. And here, when we're trying to uncover or let's say prove the existence of ancient high technology, it was very important to get a metrology grade instrument. So I settled on a Keyence VL system, which is very good, very precise. It's a metrology grade instrument, capable of accuracy and repeatability of 20 microns every time you take a measurement. But the downside was it was a rather big and bulky system, which is not possible to take it, let's say, in your luggage and check it in at the airplane when you board a flight.
How much did it weigh?
It weighs about 100 pounds because it's made of steel and heavy, heavy frame, to minimize movement and minimize distortions when you're scanning an object. But it wasn't so much the weight as the bulk of it. So it comes in a rather large box, about 3 feet tall and 2 feet wide and 3 feet deep. So I had to put it on a pallet and ship to London to a friend ahead of time. And then, when we arrived at London, we had to pick it up, assemble, and take it to the museum. And then, myself and my son, we had to carry it, two of us, through the narrow winding stairs, through the elevator, through the narrow winding pathways in this museum, to a room that was given to us for scanning, and assemble everything and scan the objects. So it was, quite an ordeal to get it there, get it assembled, get it going, and get the object scanned. At the end of the day, I'm very happy I did this because, the instrument is very high quality, and the scans that I captured reflect that. To make sure that the results were accurate, I used a size metrological sphere. I scanned it 4 times throughout the scanning process at the Petrie Museum, and every time this sphere came out perfect, and then basically is an assurance that the instrument works as intended, and it gives you the accuracy that the manufacturer states. And in this manner, I was able to scan 19 objects from the Petrie Museum collection. I scanned them inside and outside best I could. The museum staff did not allow me to turn the vessels upside down because they wanted to preserve whatever content, dust of the ages that was inside. So I ended up with partial scans of the outer surface and partial scans of the inner surface. Yet, there was enough information, enough data for me to crunch. So when we returned home to Florida, I had a huge new data set of Petrie collection objects, which were Predynastic Egyptian, primarily basalt vessels attributed to Nakada period. And I was very excited to see how those would compare to objects in Matt Bell's collection.
And what happened to the scanner?
Well, we had to disassemble the scanner and retrace our steps. Disassemble, pack, put it back on a pallet, take it to a friend, arrange for pickup, and pay crazy amount of money to have it shipped back to United States. So it was a little bit of an Indiana Jones type adventure in terms of handling the equipment. But I guess that's what you need to do when the results are important, and you need to get high quality data. So I have no regrets. I've done it, but it's difficult, and I wish there was a different way of doing it.
How long did it take you to write your program?
That's a very interesting question. So initially, when I started on this project, it took me maybe 2 weeks to write the initial code to analyze Matt Bell's collection. And then it took about 2 weeks to crunch through all of the scans. But when I came back from the trip to the Petrie Museum and ran the scans of the Petrie vessels through this code, I was surprised at the results, because before I went, I had to pick which vessels I wanted to study. So I examined the Petrie collection online, and I picked 2 types of vessels. I picked vessels that looked very well made, very precise, just by eyeballing them on a photograph. And I picked some vessels that didn't look so precise, didn't look so well made, once again by eyeballing them on a photograph. But when I looked at the scans, or rather, when my program crunched the scans, the quality metric for these 2 presumably different classes of object was about the same. So I thought, how could this be? There has to be an error in my code. So for the next month and a half, I ended up basically taking my code apart, rewriting it from scratch, modifying it, rewriting and modifying it, running countless tests, countless visualizations, just to make sure that I was processing everything right. And of course, during this process, I did fix a lot of mistakes. I did implement a lot of improvements. But it took me a month and a half of, reworking and refactoring and improving to basically prove to myself that there was nothing wrong with my code. Granted, there were some inefficiencies and, there were some minor mistakes, but the main outcome remained the same. So these objects at the Petrie Museum, they weren't a good one and bad ones, as I thought they were. They were all one class, one consistent class of objects that is characterized by about, the same quality metric, which is nowhere near the quality of modern objects. So if you take this object, which is a basalt object, very similar to the ones I scanned at the Petrie Museum, very much representative of what they look like. So this object, which is a Naqada period Predynastic Egyptian stone vessel, is very different from a modern object that's made on a lathe in terms of quality. So this is extremely precise, and we're talking, precision on the order of 1 or 2 thousandths of an inch. And this is, far less precise, and we're talking precision on the order of 10 or 20 thousandths of an inch. So there is a big difference. So I was surprised to see that all objects in Petrie collection were like this, and none of them, really matched the precision of modern objects. And that was an eye-opening revelation, which made me, reanalyze Matt Bell's collection.
Study books for the course. Yeah.
Because
Absolutely.
out of 99 amateurs, it would be 1 or 2 people who know what they're talking about.
Yeah.
And that's how I, get blanks filled in my background, because I don't know much about geology. Eventually, he's handling, of nuclear waste. Like he was saying in the time of Djoser, there were a bunch of Earths might have a trivial explanation. These objects are, contaminated. So,
How do objects from Matt Bell's collection compare to the vessels that we scan in the Petrie Museum?
it's a very good question, because the unusual findings, unusual results from the Petrie collection prompted me to rerun my newly updated and revised code to reanalyze Matt Bell's collection. And once I did that, I noticed that objects in Matt Bell's collection cluster in 2 distinct clusters. One cluster was very consistent with modern objects. Basically, 10 or so objects from Matt Bell's collection had properties very similar to objects machined nowadays on a lathe. I would say practically indistinguishable. And the rest of his collection clustered in the same way the objects from the Petrie collection clustered on the quality chart that I built as a result of my analysis. So about half of his collection is consistent with modern machining, and the other half, or 2/3 of his collection, is very well consistent with the Petrie Museum objects. And that was a stunning revelation for me too, because I realized that I can use this methodology, the metrological analysis that I developed, to apply to 3D scans and pass a judgment on how the object was made. And if we know how it was made, we can tell when it was made. So it seems that the analysis allows us to tell objects that are made nowadays using very high precision lathes from the manually made objects, which we attribute to the earlier years when people chipped and chiseled at the objects. So which brings another interesting question. If this is the case, then what about the claims about stunning precision of the Predynastic Egyptian ancient objects? My answer here is twofold. On one hand, I didn't see this precision manifested anywhere in the Petrie collection objects. They are basically consistent with the manufacturing by eye and by hand. So whoever made them, were eyeballing the objects, and they made them by hand. because if you make something on a lathe, the quality and metric is far different from what I've seen at the Petrie Museum. In the same time, there was, one particular metric that cannot be easily explained by manual labor, by manual manufacturing process, and that's, the roundness of the inner surface of the Petrie Museum object. So where the outer surface looks nice, but it's not machine made, the inner surface, clearly displays striation that are consistent either with lathing or with boring. And even though these striations, in principle, are the same as the ones that you get when you use, let's say, a tubular drill, the roundness of them is inexplicable by manual labor. So the inner surfaces of the Petrie Museum objects were machined in such way that that the material was removed in perfectly round, perfectly circular sections. And that cannot be done by hand. Origin, ancient Egyptian origin. And I wrote some code in MATLAB to analyze how to say, cut it into slices, you get circles.
Yeah.
And those circles were so round and so concentric that I basically couldn't distinguish any deviation from perfection. And we're talking, 10 micron level.
Yeah.
And because in my line of work, I order machine parts, and I know what it takes to machine.
Yeah.
And the question becomes, how the heck can you do it? How the heck can you do it in stone? And the biggest question, why? Because I also bought some contemporary, like gift shop vases, because they make them. And I'm sure of it because I wanted to expand the samples of the objects to compare against. And I came across these alabaster vases that are made presently in Egypt. They're made for tourists using, the same millennia-old techniques that, we know ancient Egyptians used. So ancient Egyptian alabaster making techniques are very well documented, very well known to archaeologists, because there are depictions on the tomb walls in papyri of stonemasons cutting these stones, cutting alabaster, hollowing it out, polishing it by hand. So we know how similar objects in ancient Egypt were done. So nowadays, artisans in Egypt use the same exact approach to produce this, museum replica vases for tourists, and they're entirely handmade, and they're made, using the same techniques, as Egyptians used for millennia. So when I bought a bunch of these and I scanned them, I was surprised to see that the quality of these alabaster-made, handmade objects is exactly the same as the quality of the objects at the Petrie Museum, which convinced me that, we're dealing with the manual labor, where the object was clearly chipped and chiseled by hand and clearly polished by hand. What I cannot explain by hand, though, is how the object was hollowed out, because these alabaster-made objects, their inner surfaces is not as well made as the inner surfaces of the Petrie Museum objects. And by saying not as well made, I mean not as round. So if you take a scan of the inner surface of the modern day alabaster object, which is handmade, and compare it to a scan of the inner surfaces of the Predynastic Egyptian basalt vessel, which we don't know how that was made. So you get extremely circular slices on the Petrie Museum objects and not so circular on the alabaster objects. In fact, the circularity of the slices of the Petrie Museum object matches the circularity of slices you would get on the lathe. So we see the level of precision here that matches or rivals modern machinery. And that was a surprising observation. What was also surprising is that the concentricity of the Petrie Museum objects, of the inner surface slices, was very poor. It was much worse than the concentricity of the inner surface slices of the handmade alabaster objects, which is surprising. So the explanation that I could think of is that however the ancient Egyptians hollowed out, these objects, they didn't do it on a lathe. because if you did it on a lathe, you would get perfect circularity and perfect concentricity. But because we're seeing perfect circularity and rather poor concentricity, I think they must have used some kind of a handheld tool to do it. But the trick of this tool was that it was able to eat through stone very, very quickly, very, very rapidly, because if it was slow to grind through the stone, you wouldn't get this perfect circles. So therefore, I still believe that there was some ancient technology that is unknown to us, that is absolutely not understood, and that pertains to how they hollowed out these vessels. So I think they used some tool that was able to cut through stone quickly, and it wasn't emery or corundum or diamond. It could have been a diamond wheel, but then diamond wheel would give you radius that is consistent. Or if it was a tubular drill, you'll get a core of the same radius. But they were able to hollow out these vessels, and the radius changed as the vessel expanded. So whatever tool they used, it was capable of working different radii, and every time the radius expanded, you get this perfect circle, which is only possible if the tool was cutting through stone like through butter. That's how I think of it.
So what you are saying is that the ancient Egyptians used some sort of a handheld tool that carved out the shapes perfectly, but they didn't carve them out from the outside perfectly. Is that what you're saying?
Yes. So basically, the outer surface was finished by hand. And here's another good example. So this is a vase made by Jacob Avian, who is a stone craftsman in Egypt. And this is a hard stone vase. This is not alabaster. This is a hard stone.
Talk to me about the hardness of the stones. What's the difference between the basalt and the alabaster?
Yeah, so alabaster is very soft. On the most scale, it's like 3 or 2. So it's easily worked by hand. You can use a rubbing stone or a file, and you have no problem shaping alabaster.
Or use an ancient Egyptian carving tool.
Yes, or you can use an ancient Egyptian carving or boring tool to work alabaster, no problem. Exactly like archaeologists tell us it was done, and exactly as Egyptians themselves depicted it. But if you take, let's say, basalt or granite, and these are much harder. We're talking most scale 7. And these stones, nowadays are machined using, diamond, basically diamond discs, diamond saws, diamond tipped, whatever.
Because nothing else can cut through the stone?
Well, you can, but it will take forever. And the assumption here is whoever does the work, it's a rational person. And rational person, wouldn't spend 2 years on a vase when there is a softer stone. So alabaster, you can shape it in a matter of days. If you wanted to make the same vessel out of granite, it can be done. And Olga showed us clearly it can be done, but it takes far longer. It took her 2 years to make her vase. So nobody, rational or sane would spend that much time when you have a softer stone. Besides, alabaster and travertine and marble looks nice, a lot nicer than basalt. So why would you take, ugly basalt rocks that are black and unpleasant, have no aesthetic value, and commit 2 years shaping them?
Yeah, that makes sense.
But the point I wanted to make about this, so Jacob made this vase. He made it using power tools, modern power tools, specifically angle grinder. So he machined it, out of hard stone and polished it using the angle grinder. And it looks nice. It looks very, very fine. But when I scan it, I see exact same quality as of the alabaster vase that was made by hand. So the point here, power tool does nothing to the quality of the resulting shape, because you still hold the tool by hand. You still use your eye for a measurement device. So you're still relying on your hand and eye, whether or not you're using manual tool or a power tool. So the resulting outcome is the same in terms of precision. So when I scan this vase, I get the same result as this vase. They are indistinguishable.
If you'd like to learn about Nakada period or the Predynastic Egypt, visit my blog. Link is in the description below this video. So when we went to the Petrie Museum and saw their collection of pottery and stone vessels and many other items, what was the surprising fact that drew your attention to the stone vessels?
Well, the most surprising thing was the realization of how weathered and how beat up the objects in the Petrie collections were. Even when they looked nice on a photograph, when you actually handled the object, you could see how weathered its surface was. So the objects really looked their age. They looked like they were thousands of years old because of erosion and various imperfections on the surface. And many objects were damaged too. And that was kind of the most stark contrast from the objects I've seen in the private collections. So the objects that are privately owned tend to be, much higher quality. In fact, many of them look like they've been made yesterday, which obviously, raises question about, their authenticity. They just, didn't look their age, whereas objects in the Petrie collection were, clearly much weathered and imperfect in that way.
Was there a very specific pattern on the stone vessels, or describe the weathering? How did it look like?
Well, besides the discoloration of the stone, so the discoloration would be, the obvious one. But besides discoloration, there would be pits and, missing grains, cracks, things of that nature. So the surface of the stone kind of looked rough, like surface of a rock that you find outdoors. You go for a walk somewhere in the mountain, you find a boulder and, you run your hand against it. And even though, the surface overall looks smooth, but you feel, with your fingers, it's not so smooth. It's been weathered by rain and sun and whatnot. So Petrie Museum objects, had a lot of that feel to them. So
what you're saying that they were not shiny at all?
No, they were not shiny,
What else did you notice about the stone vessels?
Well, I noticed something else rather interesting. Like some objects had an awkward foot attached to them. And what I realized when you look at a picture of an object with a foot, the object looks crooked because the foot is crooked, whereas the rest of the object is near damn perfect as the hand and eye allows you to make it. And that made me realize that the foot was not intended to be a part of the finished object, especially because I've seen several objects that look exactly the same, except one had a foot and the other didn't. So I think the foot was used to clamp an object either in a machine or in a sort of a vise when this object was shaped. And when the object was finished, the foot was cut off. And that would explain, this awkward, crooked feet. And besides, there was one object there where a foot was so small, it couldn't stand on it. So it's clearly, made for clamping. But I'm certain they didn't use this to clamp like in a chuck of a lathe, because even for objects without handles, the outer surface wasn't, machined on a lathe. It was still consistent with manual machining. But the inner surface, is a different story. So maybe maybe they clamped it by the foot when they machined the inner surface somehow, but that part I'm not certain of. I also want to mention that, when I told this to Matt Bell, he had a brilliant revelation about the mace heads. So there are plenty of mace heads in various Egyptian museums, Egyptian collections, and those mace heads make no sense because they have this conical shape to them. But the character of stone, the texture and the color looks exactly like stones from ancient Egyptian vases. So he said, well, those mace heads are leftover feet from the other vessels that were finished. And once he said that, everything kind of clicked and fell in place. I do believe now that those conically shaped mace heads are leftover feet from the finished vessels. And because there were thousands of vessels made, there are thousands of leftover feet. And all the Egyptians had to do when they found them was, drill a hole through and, put a stick and you have a mace head. And the rounded mace heads, in all probability, aren't mace heads either, but are starting points for shaping of the stone vessels.
Yeah, I think it's a brilliant idea. Okay, so it looks like you spent a year working on this project. What would be your conclusion about the pre-dynastic Egyptian stone vessels?
Well, I can say several things now that I've studied the subject in considerable depth. I'd like to think that I've developed a metrological analysis technique that can examine any scan of any rotationally symmetric object and determine the quality of manufacturing. And using this technique, it's easy to distinguish objects made using high-tech tools versus objects made using primitive tools. Or even within the tools in the same category, it's easy to tell whether the object was carefully made or carelessly made. So I think this technique allows to tell genuine handmade objects apart from obvious machine-made forgeries. But that aside, returning to the question of Predynastic Egyptian stone vessels, I cannot speak about all the vessels because I've seen only a limited set. So I've seen only objects from the Petrie collection. So I can speak about the objects from the Petrie collection that they appear to have been handmade, unquestionably handmade. Where the mystery remains is how they hollowed them out, because hollowing out of these basalt vessels is inconsistent with manual labor. It's inconsistent with lathing either. So it had to have been some hybrid tool, handheld tool they used to hollow them out, but this tool had to have a high-tech thing about it to where it was able to cut through the stone rapidly and leave this, perfectly circular marks inside, or rather, take the stone out in perfectly circular swashes that, we cannot do with modern tools unless it's a lathe or unless it's a diamond tip, grinder. But in this case, your radius would be constant, whereas in the ancient Egyptian case, the radius was changing as the object, to follow the object shape. So it's not clear how that was done, but it wasn't done entirely by hand. So some sort of unusual tool had to have been used for that. So that's what I'm interested in researching further, and that's why I'm interested in visiting more museums and scanning more objects from museum collections to see what else I might find that will tell us about the ancient technology that the ancient Egyptians or other peoples used. And here is another main point I'm going to make. So I'm going to formulate a hypothesis. So I don't believe that these basalt vessels were made by Predynastic Egyptians. I think they are heirlooms of hitherto unknown civilization or made by some other people that I will call, culture X. I think we're seeing clear evidence of culture X that was more technologically sophisticated than the Predynastic Egyptians. And I think they made these objects and Predynastic Egyptians simply appropriated them because they found them.
So what makes you think that the Nakada people couldn't have made these stone vessels? Mainstream archaeology tells us that they did carve out the stones.
Well, there is no question that you can carve a stone by hitting it with another stone. And when we review the literature, the published literature about Nakada period, we know that the people who lived then, they used flint and chert tools to cut, to carve. And it's been proven by stocks that you can use flint to scratch granite. And with some effort, you can use flint chisels to shape granite and basalt into intricate and more precise shapes. And there is no question that, and if you wanted to spend 2 years on a rock, you can shape it pretty well. I doubt this is how it was done for the tens of thousands of the basalt vessels that were found that are attributed to the Nakata period. Not just because there is a sheer number of these. So did they spend like 2 years on each vessel? That just sounds ridiculous. But the really, I'd say, smoking gun that they didn't do it comes from how circular the inner surface of these vessels is. You cannot do this, with flint. You cannot do this with chert. You cannot do this with any other stone. In fact, you cannot do it by hand. It had to have been some sophisticated tool that was able to carve out the interior in these perfect circles. And that's just incompatible, not just with the Nakata people, it's incompatible with any kind of primitive hand chiseling. That's why I think these objects belong to some unknown culture, let's call it Culture X, and they use some other technology to do it. I'm not saying they use CNC laces or laser guns. I don't know what they used. Maybe they softened stone, maybe they summoned the magical spirits. I have no idea. All I can see is the traces their tool left. And those traces are not the same traces that a chiseling on a chert or chiseling on a flint would leave. So that's the main outcome.
What would you like to do next?
I would like to study more of the objects from the museum collections. So I would like to go to some other museums and scan and analyze the 3D scans of these objects to see if they were made in the same way. Or maybe we'll find other objects that are going to surprise us by revealing even higher precision. Who knows, if we visit more museums and look at more objects, maybe we'll find vases that were made on a CNC lathe. There is no way of knowing until we actually go in and measure. So that's one thing I want to do. The other thing I want to do, I want to continue doing radiological study on these objects to verify and find evidence or prove or disprove my nuclear machining hypothesis, because I hypothesized that maybe there existed a culture that was capable of advanced nuclear knowledge, and they were able to use radioisotopes to soften the stone. And once the stone is softened, then you can machine it using conventional means, because it becomes as let's say as soft or softer than alabaster. But so far I don't have any evidence of it, but I'm not done. I'd like to capture more gamma spectra to see if I can find any technogenic isotopes or other interesting signatures that would be supportive of the nuclear machining hypothesis.
If people would like to reach out to you and help you carrying out this project, where should they go?
Yes, if you want to contact me, go to my website, which is maximus.energy. Once again, it's maximus.energy. So I have a blog called Ancient Egypt, where I post the results of my research, and my contact information is on the website. And if you like my research and if you'd like to support it, donate to the research through PayPal. The contact information is on the website.
And your blog is absolutely free, so anyone who is interested in these ancient stone vessels could go to your blog, subscribe to it, and receive information as it comes out.
That's right. Thank you very much for watching, and reach out if you'd like to know more or if you would like to help. Thank you so much.
Ta-da!